Hello YouTube, today we're going to be talking about hypothesis testing in statistics, and this is pretty much a mathematical way to show or further explain why your hypothesis or something that you have assumed may be true. So you have something that is believed to be true and something that you are trying to show. So this null hypothesis is something that's already true, maybe, and usually in statistics when we're talking about comparison, it's generally that there is no difference, that the two things that you're comparing are the same. And the alternative hypothesis is kind of what the researcher is rooting for, and you're suggesting that there's a difference. So the null hypothesis is abbreviated as H naught, and the alternative hypothesis is abbreviated as H sub A. So again, that whole alternative hypothesis is like the research, what they're rooting for. Your alternative is, I think it's this because, and now I'm going to prove it statistically. Well, you're not really proving it, but you're showing it to show mathematically. So this is kind of, it's kind of hard to grasp at first, but here's something that really helped me understand it was the innocent until proven guilty concept when it comes to law. So this is kind of, we can talk about our hypothesis. We have proven being specifics is the statistics way of quote-unquote proving that you are innocent or guilty, and we have mathematics to support that as justified proof. So we have our initial or a null hypothesis and our research hypothesis, you could say, or all alternative. So our null hypothesis is that you're innocent. We are assuming you are automatically innocent unless you are proven guilty. So statistics is that proven guilty portion. You're trying to show that something is, I guess, true or not, or you're trying to show something. But we assume that there is no change or something there. Like you assume that you're innocent. It's that assumption. If you were guilty until proven innocent, that whole system would be flipped. So just kind of think about it in terms of law in most countries of that innocent until proven guilty concept. So we're going to have just an outline of how you're going to undergo hypothesis testing when it comes to calculations and statistics. So you're going to assume when you're comparing two things that the two samples have no difference. They're the same. Then your alternative hypothesis or your research, you're saying, no, there is a difference. I really think that there is a difference between these two samples. So the first thing you do is you have to define your alpha. And this is upon your own choice, your own volition. You say, I want a 90% confidence interval. That suggests that your alpha, which is the 90%, so that 10%, which makes it 0.1, is your alpha. And that's up to the researcher. And you have your graph that would look like this, and you're saying, okay, here is the outskirts here that we're not going to be paying attention to, and our alpha over 2, since we have symmetry for a normal distribution, then we have 0.05, excuse me, or 5% on each tail. So the second thing we're going to need are our critical values, and our critical values we're going to be using pretty much are those t and z variables that we look up in the table to get those values, those statistics, to determine where exactly these occur. And those are the critical values located on the graph there. And pretty much what we're saying here is how far from zero, like how far from no change does that claim that the data has a difference? Pretty much saying, is it really far enough away to really show that there is a difference between these two populations or samples? So that third part, which is highlighted in orange, is that rejection region, which is that 1%, which is our alpha in this case. And this is saying like the outliers, like these are the ends of the thing. These are what we're allowed to reject for our data. And finally we have, or not finally, but we have test statistics, which I'll get into is how we calculate. And then finally we will get a conclusion based on the data we have. So this is kind of just an outline of how you will approach a hypothesis kind of testing problem if you want to see if your hypothesis is justified. So here's an example. We have blood pressure as either normal or high, and you have this sample size of 38 and 45 for normal blood pressure and high blood pressure, and the average blood pressure, the sample mean is 107.9 and 168.2. And the standard deviation for the sample is 16.1 and 31.7. So your null hypothesis, you're saying these are the same. There is no difference between, say you're given a drug that decreases or increases your blood pressure. From the looks of the data, it looks like maybe there is a significant difference that people have higher blood pressure in the second population. Maybe they were given the drug or whatever, for some reason, if you wanted to increase your blood pressure. So then you have your research hypothesis, which says that there is no difference, or that there is a difference. And another way to rewrite this is that there is no difference. Mu1 minus mu2 is 0. There's no change, nothing. And here is saying, no, there is something going on, either in this direction or that direction for your research. So you're trying to prove that, or justify, something is different here. So this is something, these are competing hypotheses. That's something very worth noting. But one thing to say is that your alpha is chosen. In a problem, it may be given to you, but the researcher, if you are the researcher, you will choose your alpha. So having an alpha of, say, 0.01 is a 99% confidence interval. And since we're dealing with our sample size, for this purpose, we're going to consider large, the definition of large, to be larger than 30, a number larger than 30 for a sample size. So we would be using a z-statistics. However, the general rule when we do test statistics, which are in the part 4 here, we're going to have to use t-statistics. So here is the formula when you're doing a null hypothesis, when you're comparing two means, to determine that test statistic. And to kind of, if you can't grasp that or remember it, t-statistic, or test statistic, think t, like t-test, t-value. So pretty much what this is saying is how many standard errors are we located away from the actual value, or in other words, how far away from they are each other. So here is the graph that we're looking at. So we want less 0.5% on each end of the tail, and if we convert this to a normal distribution for our values here, we can observe the change here. So to calculate that 0.005, we're going to have to use our t-table here, and I highlighted that 0.005, or 0.5%, which is located on the top here. But since we have a large sample size, as I talked about earlier, we can assume that it has a normal distribution, standard normal, so we can go all the way down to the infinity portion for your degrees of freedom and put that number down 2.576. Now this is one way of doing it. Notice how that 2.576 is also your z value as well, just worth noting because of that large sample size, but depending on how you get your data table, you should end up getting that 2.576. Now that would be true on both sides. Now you have the plus minus for that separation for symmetry. So these are our critical values. And one thing to note is that the orange region does contain that 1%. So again, our alpha over 2 is 0.5%. So now we go back here and we use this formula in the box here. And we're going to compare the two means. We'll have normal be mu1, or excuse me, y bar 1, and then high y2 bar. So you compare the two differences at the top. You can plug in the standard deviations and square it and divide it by the sample size and take the square root, put them over each other, and you get this value of negative 11.7. Now, we're going to see how that looks like on the graph here. Negative 11.7 would be like way out here, and then the opposite would be positive 11.7, which is way up on the other end. So now the test value here that we just found out, it determines if it lies in the rejection region. That means it's greater than, or depending on where you're looking at it, but it's in the rejection region. So if we're looking at the positive section here, 11.17 is greater than 2.56. It's in the rejection region. Therefore, we can reject this null hypothesis. So if your variable, if your test value lies in the rejection region, you reject your null hypothesis. If, say, it were on the inside, more towards mu equals 0, then you would have to not reject the null hypothesis. You would not reject it. Now, one thing to note is that this is a binary outcome. So what that means is that it's either you reject or you accept kind of thing. You reject or accept. It doesn't matter how far away it is, pretty much. If you had 3 as your test value instead of 11.17, it would still be rejection. Like, oh, we have to totally reject that? No, that's bad thinking. It's one or the other. It's reject or deny. Or reject or accept kind of thing. So even if it were at 3, it doesn't matter how far away those are. It's just one or the other. And sometimes students get confused and they're like, oh, because I have 11.17, I can totally reject it. This is like way off. No, that doesn't mean. This is just a statistic way or a mathematical way of showing this is rejection or acceptance of the null or of the null hypothesis, for example. So let's go back here. Remember, we wanted to see if these two populations differ. So what does this rejection of the null hypothesis mean? If you told someone that, oh, I reject your null hypothesis, well, how do you explain that to the common individual who might not know much about statistics? Well, rejecting the null hypothesis, in this case, we're looking at normal blood pressure and high blood pressure. So, since we assumed that there is no difference, we said, oh, the null hypothesis, we're saying that normal blood pressure and high blood pressure have the same value here in this case. Well, since we're rejecting that, that means the population with normal blood pressure and higher blood pressure do have different means that are not equal, that don't have the same mean. So pretty much we're accepting this research hypothesis. There is a difference going on here. Either the addition of a drug or whatever they used, or whatever was being tested here, does have an impact on blood pressure, being categorized in normal or high, whatever, on each sample for each population. So that's what you're saying, there's a difference. That is the rejection of the null hypothesis when you say that. There's a difference. You're accepting the alternative hypothesis or the research. This is the idea the research is rooting for. You can say like, oh, they want to have a difference, so this turned out to be so. Hope this helped understanding hypothesis testing. Pretty much to summarize, we use this outline here to mathematically say that we either reject the null hypothesis and accept the alternative or research hypothesis, or the opposite. So pretty much this is the mathematical way of justifying your answer when it comes to making to justifying your hypothesis. So I hope this helped, and good luck practicing.